Thank you everyone for coming today. Today we have Professor Ren to talk to us about fault tolerant consensus. So take it away.
All right. Yeah, thanks for inviting me. And it's a pleasure to be here to tell you about this problem I have been working on called fault tolerant consensus. It's a pretty old problem in computer science and also one of the most fundamental and application and sees a lot of applications. And it's first introduced in the 80s. And the researchers who defined this problem gave it a pretty cool name and cool story to make it more fun. And it's now called the Byzantine generals problem. And the story is set in medieval time. Imagine we have a bunch of generals from the Byzantine Empire. They each led their armies to lay siege on the city. So now they want to agree on a coordinated battle plan. Either they all attack or they all retreat. So far this problem may sound pretty easy. What makes it difficult is that it turns out some of the generals may be traitors. And I think initially the authors picked Byzantine Empire and Byzantine generals because it's they somehow get the reputation that the Byzantine generals are treacherous. And so now suppose we have one of the general being a traitor, and he would like to try to disrupt this agreement and try to disrupt a coordinated battle plan. For example, he may say one thing to one teammate and say the opposite to another general. And now our goal is to have the loyal generals somehow talk to each other and figure out and still agree on this common battle plan. And now in this particular case, you may think, so if the two generals at the bottom talk to each other, they would realize that the top general, the gray one, seemed to have lied, and maybe they can exclude him from the decision and reach and negotiate a battle plan between the two of them. Right? But it turns out it's not that simple because from the perspective, this general on the right, it could have been the case that the real traitor is the person on the left. Right? And the top general is actually honest, and it is saying the consistent thing to both of them, but this other general on the left is trying to accuse the top general incorrectly and try to drive them and drive them apart and try to discredit the other general. And in fact, this problem now becomes pretty difficult. Right? There's actually no good solution if there's one traitor out of three, right? Unless we use some more advanced techniques that are beyond the discussion of today. Right? And this is just an example to get you started thinking about how you might approach this problem. All right, so next you may be wondering, all right, so this is a cool problem and cool story, but why is it useful? And to explain that, I'd like you to consider any service. And by any service, I literally mean any website you can interact today. We can call it a service. Like for example, if you go to a website buying a plane ticket or booking a hotel night, or if you go to your bank and transfer money to some friends, right? All of that today is handled by some server on the remote side, on the cloud side. Right? This server takes user inputs and process them and modify some states or storage or information on the server side, and then issue a response or confirmation to the users. Now, the problem with such a cloud service is that the server may fail. This is, you experience it when your favorite website is down. And how do we make sure that the server can provide uninterrupted service, well, one natural idea is to replicate it. And by that, we simply meant deploy more servers that do exactly the same thing. So in this case, if one of the server fails, you still have other servers that are serving customer requests. But now that we move to a replicated service setting, one issue immediately becomes important. That is that we need to provide some sort of consistency between the servers. Imagine that now this is a airline ticket system. If there is one last seat remaining on this flight, and both Alice and Bob want to purchase this seat, due to some random variations in the network, it could be that one of the server feels Alice came slightly ahead of Bob, and the other server feels Bob came slightly earlier than Alice. Now, if each server is doing its job independently, then we could run into a situation where one server decides to sell the last ticket to Alice, and another server decides to sell it to Bob. And that would be an undesirable situation we don't want to be in. Of course, let's ignore the fact that airlines tend to oversell their tickets these days. If they do the right thing, we do not want the same seat to be sold to different customers. So therefore, we need some mechanism for these servers to reach consensus. And that is the problem we introduced in the beginning. So we need consistency between all servers. In other words, we want them to agree on the actions they take. Said another way, we want to provide customers an abstraction or an illusion of a single correct server that never fails. Despite that, our systems actually consist of multiple servers that individually may fail. And this is the motivation to study fault-tolerant consensus. And there are usually two types of faults that we study in the consensus problem. The first one is called crash. That simply means a server goes down, either because it loses its power or because it loses its network. And the harder case is what we call malicious faults. This is when a server actually actively tries to interrupt the consistency between servers. This is when some of the servers are taken control by the adversary. And because when we first introduced the problem, it is called the Byzantine generals problem. So nowadays, we also call malicious faults Byzantine faults. Now, the easier case is crash fault tolerance, and this has already been widely used in the industry. And every big IT company you know about, like Amazon, Microsoft, Google, each has its own implementation of crash fault tolerant replication, and it is being used in their critical infrastructure every day. On the other hand, for a very long time, Byzantine fault tolerant replication doesn't have many applications, because the examples we gave so far is a single company deploying multiple machines. And in these cases, it's very hard to imagine that some of these machines are completely compromised by hackers. But nowadays, Byzantine fault-tolerant replication starts to see applications, especially with the invention of Bitcoin. It kind of opened up our mind on what consensus can do. And for a very brief introduction on Bitcoin, it is a decentralized currency. The way it does it is to observe that if we can use a fault-tolerant consensus mechanism to make sure everybody agrees on the history of transactions, then everybody agrees on who paid whom, by how much, and when, and everyone agrees on the account balance of every other person, then this system can essentially function as a currency. even though we have no physical bills or coins and bank or so on. All right, so that is my very high-level introduction to consensus and cryptocurrency. And to conclude, I just want to tell you that this problem lies at the intersection of many exciting fields in computer science, including distributed systems and distributed algorithms, computer security and cryptography. And it is a very interesting problem to me. And I would love you to spend more time thinking about it if you find it interesting. And this is one of the few cases that in computer science, we work with opponents and teammates. If you are exposed to programming a little bit, and usually the way computer science works is that you get a problem, you design a solution or algorithm to the problem, and the problem is your input and the solution is your output. And what excites me in distributed computing and security is that you're not working on your own. You have to be mindful about the teammates. We're outputting a coordinated set of actions and responses. And we'll also have to be mindful about the potential opponents that try to disrupt our algorithms. And that makes the problem a lot more fun. That will be the end of my talk. And thank you.
Thank you. One question here would be, going back to crash fault tolerance that you mentioned earlier, does this take a significant amount of resources for companies to apply when it comes to multiplicating servers that take in a large amount of traffic?
Yes, it does take some non-trivial amount of overhead. If we replicate one machine to like 3 or 5 machines, it does cost 3 times or 5 times the storage and computation. But for the security sensitive ones, and nowadays it is generally agreed that this is indeed worth it.
Okay, great. One other question we had here, are there any other applications of Byzantine fault tolerance in addition to Bitcoin that you talked about earlier?
Yeah, that's a great question. So Bitcoin, you can think of it as a decentralized currency. Right? So now with it, now people are trying to come up with decentralized other things. Right? So in Bitcoin, we said if we all agree on the transaction and the monetary transactions, then it is a currency. Now, if we all agree on who voted for whom, then we can think of it as decentralized online voting systems. If we all agree on the IP addresses of each other, then it is called domain name service. Right? So nowadays, every functionality or service you can think of, one can potentially turn them into a decentralized version, even though it doesn't always make sense.
Okay. Another question we had here would be, what do you think the future of this field or the future of fault tolerance consensus looks like with this increasingly virtual and technology world?
That's also a great question. It's little hard to predict. So my feeling is that for the type of applications that are entirely virtual, like gaming and some online events, it would be pretty natural to make a decentralized version of it, because this way you cut out the centralized authority that can drive up your prices and take like ticket fees and all sorts of overheads. But for the other type of applications that connect to real world, like if you want this to be deployed on some IoT home devices, right, or transportation or supply chain, that there usually are pretty big challenges, because the connection from real world to online world usually is a single point of failure, and it's hard to distribute the trust of that.
Yeah, so
Yeah, go ahead.
The last question, kind of just to sum everything up, for a student that's interested by your talk and wants to get started in this field, what are some skills that you would recommend they learn, or some things that you would recommend that they know to kind of get started?
Yeah, so I think the fault-tolerant consensus problem really lies at the heart of multiple directions. So it is one of the more advanced directions that you will be exposed to. So my suggestion would be to lay solid foundations on programming, data structures, algorithms, and after that, take some courses or read textbooks on security and cryptography, and you will discover many related problems and to get you prepared for doing work in this research direction.
Okay, thank you so much, Professor Ren, for talking to us today about everything. And thank you. Yeah.
Thanks, pleasure.